All right, welcome to the Blue Economy CRC webinar series for 2025. I'm Dr. Jana Osagova, the Deputy Program Leader for Offshore Renewable Systems in the Blue Economy CRC, as well as a Senior Lecturer here at University of Western Australia. So I'm really honoured to be facilitating this webinar on wave energy. So to start off with, I would just like to begin paying respects to the traditional custodians of the various lands on which we work. And I would also like to welcome Aboriginal and Torres Strait Islander people who are participating in this webinar. And I pay my respects to the elders past, present, and emerging. So a little bit of a background to the CRC. So the Blue Economy CRC was established to undertake industry-focused research and training to support the growth of the blue economy with a focus on two new industries, offshore aquaculture and renewable energy production. So now with 43 participants from Australia and around the globe, the purpose of the CRC is to perform world-class, collaborative, industry-focused research and training that underpins the blue economy. So our vision in Australia really is for the Australian blue economy industries to industries in offshore aquaculture and co-located renewable energy to be globally competitive, at the forefront of innovation and underpinned by a robust environmental planning and management frameworks that the customers can trust and value. So onto today's webinar. It's basically a rerun of 4 selected presentations from the European Wave and Tidal Energy Conference that took place earlier this year in Portugal. And so the EWTEC, conference series has been running since 1993 and really is the premier sort of biannual event on marine renewable energy that attracts developers, academics, as well as government from across the globe. So we are really lucky to have 4 presenters with us today. But before we get started, I just want to do a little bit of housekeeping. So we'll have 4 presentations, and at the end, there will be a Q&A session. If you'd like to ask a question to the presenters, please use the Q&A box at the bottom of your screen. And if you like particular questions, then please sort of thumb them up or vote them up, and they'll be prioritized, and we'll ask them first to make sure that the most popular questions get asked first. All right, so to get us started, I'd like to welcome Adi Kurniawan, who is a research fellow here at the University of Western Australia. And he's going to talk about sea trialing the M4 wave energy converter. So I'm just sorting out sharing of the screen. All right, over to you, Adi. Thank you. Can you just confirm you are able to see the slides in a presentation mode?
Yes, it's fine. Jana.
Okay, yeah. Okay, let's begin then. Thank you, Jana, and thank you everyone for coming, and also those online. Thank you for participating. So today I'm going to talk about the initial hydrodynamic analysis of the M4 sea trials that was completed earlier this year. It started at the end of last year, so it's about a year roughly since then. So this is a work of many people. So there's the project team as for a context. So it's we have researchers from academia, government, state government, local, and some end users. Maybe I should, yeah, I'm not sure how to activate the pointers, but never mind. Yeah, so we have universities, University of Queensland, Tasmania, as well as UWA, as well as industry partners, BMT, and Southern Ports Authority, and the state government of Western Australia. And obviously at the bottom here, M4 Power. And in case you are wondering what M4 is, that's the acronym for mode, multi-mode, and multi-body, and will be clear why. Okay, so the goal really is to deploy kilowatt scale WEC in the real ocean. So why M4? There has been a lot of studies conducted on this device. So if you do a literature search, you will find numerous publications on the device. The reason is because we want to optimize the technology performance level before the technology readiness level. So if you want to fail, we do it in small scale, in model scale rather than in full scale. So the survivability is relying on hydro end stop, so the dunking. When the floats get submerged underwater, it naturally limits large motion. And it is very simple. The idea is to make it maintainable. So everything that is complicated is above water. So the power takeoff is above water, and what's underwater is just simple floats. And it is deployable. It is moored by a single point mooring system. So by means of a hawser to a mooring buoy, which is easy to connect and disconnect. And it is simple. It is based on the attenuator class of WEC. So it is roughly 1 wavelength long. And it's well supported as well by, for example, the UK Research Council, as well as Australia, of course. So that's a bit of a history. So we started thinking about deploying an M4 reduced scale in real sea, I think in 2020. And then in 2021, the project was approved. The proposal was approved by the Blue Economy CRC. And the idea was really quite simple. This is a sketch of M4, which was tested in the lab, and is to scale this up 10 times and deploy it in the sea. And of course, along the way, a few things have changed, but the main dimension remained the same. So that's how it looks like just after some design iteration before going to the sea, before it is built. If you notice, we have actually made the float slightly taller. The idea, because we have a bit of a payload to sit on top of the device, and we want to provide enough buoyancy just to accommodate those equipments and power electronics and so on. And next is how the device looked like when it was constructed. This was at the time of launching. That was, so the total length is about 24 meters and the total width is about 9.5 meters. And some simplification also, if you notice here, instead of having rounded floats, we have it like segmented in polygons just to simplify the fabrication. So where was it tested? So it was tested in King George Sound. It's at the outer harbor of Albany. And where is Albany? It is about 400 kilometers southeast of Perth. That's the map of Western Australia. And that's the location where it was tested. So if you see here, it is actually protected by a headland. So there is a thin land there connecting this peninsula to the rest of the island, the continent. So yeah, the water depth here is about 13 meters, so not very deep. And what is important here is that because of this headland, the site is actually sheltered from the more energetic swells from the Southern Ocean coming from the south, which makes it ideal for this site to be a test site for a reduced scale devices. So we are looking at a scale of about 1:5 to 1:10 relative to the more exposed site, which you may want to deploy a full-scale device. Okay, and again, because it is protected from the swell, so the condition is mainly dominated by wind waves, which is coming from the east in the summertime. So that's when we are targeting to deploy this device. Okay, so this is just a zoom in of this little section here. Looking down. So if you see here, there is a little island called Seal Island. So that's where we deploy the M4. It's just close to this island. Okay, so the mooring system, it is quite simple. This is just a schematic, not to scale. So 2 hawser lines connecting the bow of the M4 to a mooring buoy. And then from the mooring buoy down to the seabed, we have just a single riser, which is pretty long. And then a series of clump weights and 3 anchors. Okay, so the timeline of deployment, yeah, roughly it was a year ago that we deployed it. So 8 November last year. And then we finally towed it back at the end of April this year. But yeah, 2 times we took the device back to shore to do some inspection and maintenance, but they are all pretty minor. So the first maintenance we did was just to replace encoder coupling, which was damaged during one of the energetic sea state that we encountered. And then the second time we pulled it back to shore, it was to fine tune the measurement of the angular speed of the generator, so related to the control aspects. But structurally, it was performing well, and it was sound. Okay, so the paper that we presented mainly focused on the first 2 deployments, so from November to February. And most of the time, the power takeoff wasn't active at this period. Only at the 3rd deployment, which was the longest, then we tried to generate and activate the power takeoff and generate some electricity. So it's a bit of an overview of the instrumentation that we put on the device. So we have motion sensors, IMUs, on the forward as well as the aft frames that provide measurements of the displacement in 7 degrees of freedom. So 6 conventional degrees of freedom plus the relative rotation between the aft and the front bodies. And we also provide redundancy. So on top of those, we have low speed encoders to measure the hinge angle. And at the bow here, we have load shackles connecting to the hawser lines to measure the mooring loads. And we have high-speed encoders inside the cabinets here, and other types of sensors, CCTV cameras as well to view the looking the fore and the aft bodies at all times. And we have, of course, onboard PC transmitting all the data 24/7. And we also have solar panels, which you will be able to see later on, and a couple of wind turbines just to supply backup power to power the sensors and so on. Okay, so from those sensors, we can plot where the device was going over the deployment duration. And you have here on the right, just a plot of where the device was. So you can see here, the device rotates about the mooring buoy, but over time, the mooring buoy also was moving slowly And if you plot the histogram of the heading of the device, where east is 90 degrees, so you can see here that the device was actually pointing to the east most of the time, even when there is actually some wind blowing from the southwest as well. And that's the displacements in 7 degrees of freedom that we plot over the 2 deployment periods. What's interesting here is probably the roll. You get maximum up to 20 degrees in amplitude of the roll. And the hinge angle, we get up to 40 degrees. So that's about, yeah, the highest we've seen. So this is a video of the M4 in action. You see this, I mean, the condition was not particularly energetic, but still you can see quite a large motion there. And just the noise coming from the gearbox, which is pretty loud. And you see here, the one in blue is actually the housing for the gearbox and the generator. And on top here, you have the solar panels. And you can see the hawser and the mooring buoy in front. And you can see from time to time, the floats actually get slightly submerged. Okay, so yeah, we have developed a model based on linear theory. So we develop it in frequency domain, where we use a generalized mode feature to model the additional degree of freedom of the hinge. So this model is able to take spreadsheet forcing as input, and then outputs the motions as well as the loads on the hinge. Okay, this is just showing the mesh for Hydrostar in utilizing symmetry of the device. And we also conducted some tank testing at AMC in Tasmania, and these are just showing some comparison of the measurements we obtained from the test with the prediction from the model, showing quite good agreement for the motion response amplitude operators as well as the power function. Okay, so the question is whether we can do the same, like we can reconstruct the response amplitude operator from the field. Obviously, in the field, it's not as easy to impose a wave as we like, and the wave is multi-directional. So what we do, we know that this relationship is true. So we have in linear system, the response psi here is related to the input, which is the wave, by a transfer function. And in the spectral form, this is how it looks like. But the question here is that we do not know the two-dimensional spectrum, because it is a function not only of frequency, but also direction. We do not know this from the field. We know this one from, we know the wave spectrum in 2 dimension from the wave buoy. So we cannot actually obtain the RAO simply by utilizing this relationship. But if we integrate the previous equation over the directions, then we have this one-dimensional spectrum of the response. And if we make an assumption that the wave spectrum is more narrow-banded in directions compared to the response, then we can actually take this out of the integral, and we arrive at a simpler relationship here, and we use this relationship to derive our RAO. because now this one is known, the spectrum, the one-dimensional spectrum of the response, as well as the spectrum of the wave. So this is a comparison of the numerical model prediction and the measurements that was obtained using the previous method. And you can see that the agreement is quite good. The roll natural period is slightly, I think, over-predicted by the model, but the range of amplitude is all looking quite good. So the search, heave, roll, and the hinge RAO. You can see that here the measured hinge response is lower than the predicted, which is quite as expected. The model doesn't account for friction, and also due to the nature of the approximate method, there should be some scatter that we expect from the data. So we miss the peak here. Okay, this is some footage from the CCTV cameras. Yeah, this is one of the highest, actually the highest hinge angle observed. So just 2 weeks after, well, less than 2 weeks after it was deployed. And you can see here the significant wave height is not really extreme, but you can see, yeah, because of resonance and the condition was just right to create such a large response. And that's the time series of the mooring load. And the maximum load that we observe actually comes from the third deployment. So it was up to 3 tons. And that's the significant wave height when that happened. And that was not coinciding with the largest hinge angle observed. Okay, so everything working so far as we predicted, but there was one surprise that we didn't anticipate before. And this is what happened. When the condition was calm, when the wind was light, actually the device was drifting forward. And as a result of that, the hawser line wrapped itself around the bow float. So that's the bow float and the hawser, one of the hawser line wrapped itself around. So one time we had to call the tugboat to release this hawser. But I think another time when this happened, it managed to unwrap itself. But of course, this is not something desirable. So as a so to prevent, well, we can't actually prevent that from happening at this point. But to prevent this rubbing against the float, we install some kind of sleeve to protect the hawser. Okay, so as a conclusion, so in terms of hydrodynamic behavior, it behaved largely as we expected. And we have also shown that the test site is well chosen. There is some challenges working in wind waves due to the high spreading, but despite that, we have shown that the approximate analysis that we did manage to recover the RAOs, and they compare quite well with the prediction. So yeah, analysis is still ongoing to more in-depth analysis, especially integrating the hydrodynamics and the power, the result from the third deployment, where we have more data on the power aspects. And the goal, of course, is to release the data and make it public. So stay tuned, and hopefully we have opportunity to redeploy this device in the future. Yeah, thank you very much.
Thank you very much. That was great to get us started. I would just like to remind everyone to, if you'd like to ask a question to Adi or any of the other presenters, please use the Q&A functionality in Zoom. All right, so we're going to move on to our second speaker, who is James Thompson. He's a PhD candidate at Griffith University, and today he'll be talking about estimating nearshore wave energy converter impact on beach width using satellite data. So over to you, James. Thank you.
Thank you. Hopefully you can all see the screen and hear me. Cool, okay. My name's James. I'm a PhD candidate at Griffith University on the Gold Coast. I work with my team of supervisors, Nick Cartwright, Amir Edamad Shahidi, and Guilherme Vera da Silva. And this talk is one of the chapters of my thesis, which looks at estimating nearshore wave energy converter impact on beach width using satellite data. I was lucky enough to present this in Portugal this year and learn a lot from all the other experts in Europe and in Australia and all over the world. And hopefully I can share some of the work from my team today with you guys. This slide was mostly for the European cohort, but I think it's important to know that Australia's got a real advantage in the wave energy space. And we have a highly coastal population, about 87% within 50 kilometres of the coast. And we have one of the largest wave energy resources globally, particularly on the southern coast from WA through to New South Wales. Of course, in the coastal space, there's growing concerns about sea level rise, severe storms, and climate change. So looking at the coastal processes along our coast is really important and how they impact our beaches. So this study looked to merge those ideas, looking at wave energy converters and their potential coastal impact as an important part of understanding how they might affect our beaches. There's been a lot of research in this space already, and I've got some of the results from some of the review studies in this space here on the screen, as well as the other study that's actually gone out and measured some of these results in the field, which was done in 2018 by Australian researchers. They found that there could be a reduction in the wave height behind wave energy converters, as might be expected, measuring a 20% reduction at 40 metres downwave and then 12% at 80 metres downwave. We wanted to take that further and look at what the potential effect on the beach might be. So things like longshore currents, sediment transport, and beach width. So the review studies out there have quite differing opinions, I guess, on this space in the field. Some studies think that the impact on the beach is pretty negligible and not worth considering much further, as wave energy converters are really small at this stage. Other studies have investigated wave energy converters as potential coastal protection structures, inherently sort of saying that they will have a significant impact on the beach, whether that be positive or negative for the communities. So we wanted to try and get some measured field data, and we found an opportunity in a recent Australian deployment. So we wanted to investigate that. The deployment we focused on was the UniWave wave energy converter that was in Bass Strait on King Island. This is an oscillating water column, relatively large structure at 14 metres by 24 metres. And it's a concrete structure that sits on the seabed and was pretty close to shore at about 100 metres offshore in about 4 to 6 metres of water. And for that reason, we thought it was a good case study to look at the potential impact on the beach. And it was in the water for just over 2 years, from January 2021 to March 2023, which gave us an opportunity to look at its effect over sort of a whole year or a couple of years and all the seasons, which we thought was really important for this study site. My talk's not going to go into any of the power or, I guess, the field studies that were done on this device. I refer people interested into how this wave energy converter performed to this study that's on the screen, the Rolano et al. 2024 study, as well as some others that look at this 2-year demonstration in a bit more detail. I'm interested in the coastal processes around this device, so it's important to understand the study site from the geomorphology and coastal science perspective. So it's a sandy beach, about 1.3 kilometres long from the southwest end to the eastern end. And to look at it in detail, we drew transects along the beach every 50 metres, as you can see here on the screen, from 0 metres in the southwest through to 1,200 metres in the east of the beach. And the wave energy converter was placed right at the eastern end of the beach near the port at transect 1200. So that's the one we're going to be focused on today. We looked at the beach before the wave energy converter went in, using 30 years or so of satellite data to get an understanding of what the natural variability of beach change was for all these transects. For the transect of interest, we found that there was quite a significant amount of seasonal variability with a natural shoreline change of about 15 metres cross shore. In the winter, we saw a more eroded beach or a narrower beach. And then in the summer, the beach naturally started to recover. We are doing more work and trying to publish a paper that investigates this natural variability, as well as this paper that was done at the European conference that looked at the effect from the wave energy converter. And by combining those two things, we hope to get a really good understanding of the impact of the wave energy converter itself. A little bit more into the methods. Sadly, we weren't able to go down and measure this beach change in person, quite a costly place to get to with a PhD budget. But we were able to employ satellite data, which gave us a really good long data period from 1987 through to the present day, with accuracy of about 7 to 13 metres of beach position. We used 556 images from September 1987 through to the end of the deployment in March 2023 to get a good idea of how the shoreline naturally varies in the pre-WEC period through to how it changed in the during WEC period of 2021 to 2023. Measuring the shoreline was done using a Python toolkit called COSAT, and this looks at each pixel of the satellite image and distinguishes whether it's likely to be water, sand, or white water. And by doing so, is able to draw a shoreline along the beach. As I showed before, we used 25 transects along the beach to get an idea of the cross-shore change over time for each position along the beach. And then for the transect of interest, the one behind the wave energy converter, we decided to do some detailed statistical analysis to compare the pre-WEC period to the during WEC period. So we did a simple t-test and difference of means, as well as a visual comparison of the kernel density estimate, and then looked at the data at both the seasonal scale and then splitting the data into all the different 2-year periods from January to March from the 1987 through to 2021 to do a sensitivity test to see if the result was robust across all the different periods. Jumping straight to the end result, we did see an increase in beach width behind the structure, as one might expect with placing the structure in the surf zone. It was a 5-metre change between the mean of the pre-WEC period and the during WEC period. So the beach became wider in that zone. And looking at the distribution as well visually, we see that that change was quite robust with significant positive change in beach width. We wanted to investigate that along the beach as well to see how it differed from other areas along the beach. And on the right here, you can see a plot from the different transects change in beach for the 2 periods from the western end through to the eastern end on the right. And this shows that for most of the beach during that period, the beach actually got narrower, except for right behind that wave energy converter where we saw that positive change in beach width. We then wanted to investigate this at a seasonal scale. We know that through the natural variability study that there is a significant difference for each season, how the hydrodynamics affect the morphodynamics of the beach. But this result held up across all seasons, with all seasons showing an increase in beach width behind the wave energy converter, in particular compared to the rest of the beach, which the rest of the beach generally became narrower during this 2-year period. We then performed the sensitivity analysis, looking at the different 2-year periods in that time frame to see how robust this result was. And we found all but one other 2-year periods to have a narrower beach than when the WEC was in the water. This gave us more confidence that the wave energy converter was a significant contributor to the change in beach width. I think the elephant in the room is that these results are based on satellite data. I think they give a really, one of their big strengths is that we are able to go back so far in time and compare the natural variability to the more recent variability. But what they lack is a real detailed understanding of the coastal processes. And I think future research should really try and get in the water and measure some of these changes to the waves, currents, as well as the beach processes around them using 3D hydrographic surveys and visualization techniques of coastal processes. Future studies should also start to look at larger WECs and how they might impact the coast using numerical modeling and other techniques. And then I think if wave energy converters are going to become a coastal protection structure, we need to understand how they compete with different options such as breakwaters or artificial reefs, which have a bit more research behind them. Through this slide in there for the community that were in charge of deploying some of these wave energy converters, I think it'd be great to see as standard practice that we start to measure some of these coastal change. And I wanted to share some of the ways that we do that at Griffith University for some of the coastal structures that are on the Gold Coast. I think the standard practice or the best practice is to get out there and do monthly surveys before you decide you're going to put anything in the water, and then more frequent surveys when the device is in the water, as well as after it has been removed. This can give us a really good understanding of the coastal processes before, during, and after deployment. Some of the instrumentation that we use on the Gold Coast is ADCPs or acoustic Doppler current profilers to measure currents, pressure transducers to measure waves, and then getting in the water with jet ski surveys using echo sounders to get depth and change of depth in the surf zone. Some more modern techniques like drone LiDAR could be really useful as well. But yeah, what this would do is would allow us to get better coastal change forecasts for future deployments and improve our coastal models and numerical models for understanding how future wave energy converter arrays might be used for coastal protection or might just affect the coast in general. So that was, yeah, I guess a short version of what we presented at the European conference. And there's the papers out there now for people to read. But in summary, we looked at the UniWave wave energy converter 2-year deployment period and measured an increase in beach width behind that device using satellite data. And we hope that future studies that are interested in coastal impacts of wave energy converters are able to get out there and do some more detailed bathymetry and topography analysis. But really wanted to highlight that an important part of this was being able to compare it to the natural variability. So getting out there and measuring these sort of processes before any device is put in is really important when you want to do a comparison study. Thanks.
Thank you very much, James. That was awesome to hear about the coastal implications of wave energy converter deployments. Okay, so we're going to move on to our next speaker, who is Dr. Jørgen Hals, who is a chief scientist from CorPower Ocean. And Jørgen will share insights with us on CorPower's sort of stage development process. And Jørgen's talk is entitled from lab test to full scale, lessons learned through stages of development with CorPower Ocean. Thank you.
Thank you, Jana. Yes, thanks for being allowed to present here. We had 3 papers presented at the EWTEC conference from CorPower, and one of them was focusing on lessons learned from our development stages. We had another paper on resource mapping for wave energy at Madeira. I'll have a comment at the end about resource mapping, which is linked to that, and also one paper on control and models used for controlling the device. But this talk will focus on the last of the papers, which was about lessons learned. So looking at the development stages we have been through. So taking us from the early ideas and seeing how, in our case, they have been evolving over the years, last 13, 14 years since the first activity in the company. So you see here some early pictures or drawings, and then the device as it looks today. The full-scale demo. I'll just take you briefly through the main properties of the system. So you can see here through the whole water column the different parts. So we have a hull, composite hull, which actually contains all of the machinery. So most of the machinery is connected to the part that is not oscillating. So kind of sitting at the mooring part. And then there is the mooring itself, which is a tension leg type of mooring. So it's constantly tensioned by a component inside the hull. And also there's a tidal regulator, which we use to adjust the length of the mooring. And then there is the power cable then routed through the mooring and coming off by the anchor head, and then this is the anchor itself, which is a pile anchor type, looking like this. And the core data for the device are listed there. So rated at 300 kilowatts. The depth where we demonstrated is 46 meters. Total volume of about 420 cubic meters. It's 9 meters in diameter, and the total mass of the system is about 106 tons. And then looking inside, you can see here, I'll just go through the governing subsystems that are most important for the functioning of the device, and that would be the retention system, which is used then to establish the equilibrium position. It's a very light buoy, so that the part oscillating is naturally floating more like a cork, and then it's pulled down to establish the equilibrium by this retention system, which is a pneumatic cylinder, the long white part there. And then we have the wave spring mechanism, those horizontal cylinders that are used to tune the system so that we interfere with the waves in the best possible way to make the power flow from the waves into the mechanical system. And then there's a gearbox which has been designed, so it's a bespoke design for this technology, converting the motion from linear translation to rotation. And then the fourth point on that list would be the control algorithms that we apply, which is of the model predictive control type. And then also the company itself, in short, so it's a company established to develop and deliver turnkey wave engine systems. It started in 2012. We now have offices in Sweden, small office in Norway, a large staff in Portugal, and 1 or 2 persons, I think, in Scotland. The goal is then to make cost and material efficient technology for this, and it has received broad backing across Europe and have been supported by 150 million euros in funding so far. So it's split between public and private funding, and there is another at the moment, more than 79 million euros that is in form of intention agreements with future customers. And the company has today about 95 employees. So let's dive into the development itself, how we have been running this. So we are following this stage development framework advised by the International Energy Agency. Starting here at stage 1, that's where we were about 2012. I'll just give a couple of pictures and some points on the content or the work that was done during that phase. So obviously the early concepts and the evaluations, comparisons between different identified solutions. Mathematical modeling was then used to estimate the power output that we could get and the loading. And we did some tank tests at 1 to 30 scale was also in Portugal, actually, in Porto, so close to where we're demonstrating now. And there was a small bench test of the gearbox, which was kind of a core component of the technology. So it very much started with that, the whole company. So that was an early endeavor, and also some evaluations of different buoy shapes. I think that summarized the first stage. I want to emphasize that it's the same as was mentioned by Adi, that we have tried to follow this performance before scale-up strategy that has been advocated by Jochen Weber in series of publications. So instead of what has often been done traditionally, is to start moving along the technology readiness scale. Make sure that you check your, so you see in the illustration to the right here, that what you should strive for is to make models and try to think about the techno-economic performance as early as possible by doing modeling, feeding that back into exploring different solutions so that you're able to climb up here in performance before you start maturing the detailed technical solutions. So that has been also the path forward for CorPower Ocean. So then moving to stage 2. So that was a couple of 2-3 years process where we developed a more complete detailed way-to-wire model, which has been crucial in all the designs. So we use that a lot to look at loads and to guide the design of the different subsystems. And we did again tank testing at 1 to 16 scale this time in France. Also made dry test, the PTO dry test, so the full machine, not the full machinery, is still focused on the gearbox, but was tested at 1 to 3.2 scale in Stockholm, 5 kilowatt power capacity. And the wave spring mechanism was introduced that I mentioned in the overview in the beginning. So that was a part of the tank test to evaluate the effect of this. And a lot of effort was put on the improving the economical modeling, so informing these techno-economic metrics that we derive, and to look ahead whether this is a worthwhile activity. So I think that summarizes stage 2. So try to move a bit quickly here. So stage 3, Then was the half-scale device. So it contained mooring design. So now we had to relate to the real world. Tidal regulation was included. We had a flywheel energy storage at that time, wave springs. So the mechanism was designed like for real for the first time. Same with the pretension system. Everything was manufactured at half scale then, and a new test rig was built, dry testing. So I think the idea has been to try to test all the components at the smallest relevant scale. So we have done a lot of dry testing, but some things are not easy to test realistically if you make it too small. So yeah, always this dry testing, which has been important. And then the ocean testing itself, which happened at EWTEC, Scapa Flow site. The dry testing in Stockholm was grid connected. The actual testing in the ocean was not. It was a standalone system. We then calibrated our wave-to-wire model, and then we could see that the understanding seemed to be good. Good correspondence between what we measured and what we simulated. And also working with DNV from this stage, the testing was done with a statement of feasibility for the half-scale test. So yeah, that was stage 3. Moving to stage 4, that's a full-scale demonstration, which we started working on in 2018, and we're still not fully finished with that stage, but a lot of redesign and modifications compared to the third stage. So the hull, mooring, anchor, retention system, wave spring, gearbox, generator configuration, all that was changed to make it more simplify, make it robust, make it moving towards industrialization, which is the point, but it's in the long run. And we did here also several tank tests at 1 to 20 scale. We had challenges with the mooring solution. Made us do a lot of tank testing to be sure that that was feasible. And again, scaled up the dry testing in Stockholm. You can see a picture there, top large dry testing rig. Also a lot of testing of seals and lubrication, controller developments, manufacturing, assembly, and dry testing of the PTO happened in Stockholm. And we manufactured the hull in Portugal and the mooring leg in Norway. Demonstrated now for the first time then grid connected operation in the ocean, and also went through a couple of large storms. The anchor solution was kind of validated to be feasible and efficient. Good correspondence again achieved between our models and what we measured. A lot of experience in the marine operations, and both improvements happened and identified for the future. And continuing the collaboration with DNV towards type certification, which is the goal then to enable commercialization in the end. So that has also been an important alliance, you could say, or cooperation to get proper feedback from a competent body. Just showing a few videos and pictures from then the stage 4. So this is the dry testing rig in Stockholm, where we imposed then the same loads to the machinery that it will experience at sea. And it gave the opportunity to mitigate problems and solve software bugs. And without this, we would have not been there anymore, I think. Here's the PTO packed and ready for shipping to Portugal. So that's how it looks, the whole PTO on a trailer. And then the manufacturing of the hull, which we do in the machine hall in Viana do Castelo, close to where we have it installed. Here you see the different parts with the PTO then moved in and then connected to the hull, and the mooring leg there in front. Yes, so all in all, after these 4 stages of development, we still think that we have a solution that can set a new state of the art for wave energy. So comparing to this study that is starting to be a bit old from Aurélien Babary and co-authors from 2012, it was a cross-device comparison to look at some performance indicators. So you used mass compared to energy output. So when we compare to that, we see that we score more than 5 times better than what was observed in that study on annual energy per ton. And we also see then that we think we can overtake the numbers seen for floating wind turbines. So we are at less than 300 tons of total mass per megawatt installed. Yeah. So and now we are in the phase of making the design for the next stage, where we will test a small array of 3 more devices, and it will happen in the same place than in Portugal. So I think with that, I'll just use the rest of my slot here to talk about a study done by Shona Pennock, my colleague at CorPower Ocean. So this is a similar study that she presented at EWTEC for Madeira, but it's comparing, or it's looking at wave energy as part of a renewable energy mix in 4 different parts of the world, to see how the different renewable sources play together in a grid where you aim to reach high levels of renewables. So it has then a combination of onshore wind, offshore wind, solar energy, and wave energy combined with storage. And this yeah, so it assumes battery storage to then enable continuous supply of power. So this slide might be a bit confusing at the beginning. Let's focus on the Australia side. So it was one, yeah, you see one in Portugal here, and then in Scotland, and it was in California and the US, and then south of Melbourne here in Australia, the 4 sites. And as you can see, the Australian both wind and wave resources are quite consistent throughout the year. So this shows an example of the variation of the resource over a year. And we estimate that with wave energy, we can reach capacity factors in the range of from 50 to 60% typically in these sites, except for Australia, where our studies show that we can actually reach capacity factors exceeding 70%. So that's quite amazing. So the study was done in the way that it first made an optimization of how the renewable sources best can be combined if you don't include wave, and then the same optimization if you include wave. And then we find that consistent for all these sites, and we can take Australia as the prime example because it has extraordinarily good numbers for this. You can see that you can both reduce the necessary installed capacity. So we assume that we want to achieve a renewable energy share in the grid of 95%, so 95% carbon-free energy, and then that could be done. Then with wave, you reduce the needed installed capacity by 43% for the Australian side here. At the same time, you reduce the levelized cost of energy and the need for battery storage. So it's a strong case for wave energy in all these sites, and in particular for Australia. So it's almost it's astonishing. And I think it's consistent with all the studies on this, but it's good to repeat, I think, especially talking to an Australian audience. And of course, this is based on assumptions about the cost price of the energy. So we have used available data for the actual price of and future expected price of solar energy and wind energy. For wave energy, we don't have any experience, so there we use our projections for the cost, and we also did a sensitivity study about that. And then we see, even if the cost of wave energy, so again looking here at Melbourne, we see that even if the energy cost ends up being like 3 or up to 4 times larger than we think, the optimization picks up wave energy as part of the mix and says that you should put wave energy in there. Thank you.
Thank you very much, Jørgen. It was great to for you to show us the journey that you've gone with CorPower. Okay, I would like to just remind everyone to please post your questions on the Q&A function. And in the meantime, I'll welcome our last presenter, Dr. Natalia Sagienko. She's an ARC Industry Fellow at University of Adelaide and has a fellowship with Carnegie Clean Energy. And she'll be talking today about wave prediction requirements for wave energy applications. Over to you, Natalia. Thank you.
Thank you, Jana. Yes, I will be presenting my work done for Carnegie Clean Energy on wave prediction requirements for wave energy applications, and it was done in collaboration with Matthew Kosha. So for people who don't know what Carnegie technology is, it's a CETO technology. It's a buoy which sits underwater a couple of meters. It is connected to the seafloor with 3 mooring lines, and each mooring line is connected to the rotary power takeoff system and then a generator. So the buoy's motion is pretty much converted to electricity with 3 generators. It's a nice video, so I'll keep showing. The problem that we had before deployment, actually, so when you have a device in ocean, you want to control it in such a way that you can maximize its power production, electrical power output, and it's usually done by some advanced controllers like a model predictive controller or reinforcement learning controllers. And those controllers, they require information about incident wave, which is coming towards the buoy. So in order to build the controller and maximize power production, we need to know surface elevation. But of course, surface elevation is not known perfectly. We need to predict it, we need to measure it, we need to predict it, and so on. And the question is, say, if we want to develop such a predictor, what should be the requirement for the wave elevation prediction that the power production stays within satisfactory boundaries? So the question that we had again, what is the correlation between electrical power output and wave elevation prediction? So for this study was done purely numerically. As planned, we used CETO system. Controller was a model predictive control. In this study, we haven't varied MPC parameters. They were fixed, like prediction horizon and some other parameters. They were fixed and optimized based on previous performance. And in terms of the numerical model, we used the wave-to-wire model built in VACSIM. And that model does not just account for hydrodynamics, but also account for the power takeoff dynamics, drivetrain dynamics, and losses in the generator side. So in terms of the performance measure, the companies who develop predictors, or even like researchers who develop predictors, they work with such a measure as a normalized root mean square error. And this is just a root mean square error, which is normalized by the significant wave height of that sea state. And the question was that I needed to come up with a magic number or prediction error threshold that will be allowable for maximum 5% drop in power. So 5% drop in power just came empirically from the company requirement, technical requirements, and I needed to come up with the number of the wave prediction requirements that can be given to the wave prediction developers. In terms of okay, we have a problem, but then we need to model the wave prediction error somehow. And we came up with 3 different possible sources of the wave prediction error. The first error might be as a time delay. So time delay not necessarily might be coming from the algorithm itself, but it just can come from the connectivity or data acquisition issues or so on. The second source of error that I investigated was the bandwidth, and it's mainly coming from the prediction algorithm itself. Say the wave predictor accurately works with particular wave periods, while outside that band does not predict perfectly. And the last source of error was noise. Noise can be coming from either measurements or prediction algorithm itself. So that's 3 sources of errors we came up with, and then we have done a detailed sensitivity studies. So the first source of error was the time delay. How I model time delay simply, so the wave elevation which comes to the plant is just the same wave elevation comes to the controller, but is just delayed by some value delta t. And on the plot, you can see just an example of the true and predicted wave elevation signals. And for this particular example of the sea state 1 meter and 10 seconds, the time delay of 1 second leads to about 90% prediction error if measured in terms of normalized root mean square error. So the first bit wanted to understand what is the correlation between the time delay and prediction error itself. So prediction error is proportionally has a linear dependence on the time delay, but it for shorter peak wave periods, the error is increasing. However, it's just like divide the time delay by the by the TP, we can get just clear linear relationship between the prediction error and the phase delay. So next, we understood how error depends on the source of error. So NRMSE depends on the source of error as a time delay. And here I'm showing like it's a bit busy plot, but how the normalized electrical power depends on the prediction error itself. So, and different curves correspond to different peak wave periods, and 4 plots show different significant wave heights. So, dotted line is our magic threshold of 95%, where we would like to keep our power production within the bounds. So we can see that for higher sea states, prediction error does not significantly cause drop in electrical power, and it's mainly due to the reason that constraints kick in, mostly motion constraints start playing a role. So we are not losing that much power from the time delays. While for HS, say 1 meter, we can see that we can handle about less than 10% the prediction error, and then power drops significantly. Also, what we can see that power drop has a kind of quadratic relationship of the time delay. And also we found that for this particular case and for this particular plant, the time delay of around 0.4 seconds can be acceptable. The next source of error that we investigated is a bandwidth. Say the predictor accurately predicts within the particular frequency range. And in this example, I'm just showing say the prediction is accurately within 10 to 12 seconds peak wave periods. And the wave prediction, which is used in the controller, the spectrum of that sea surface elevation is just scaled down from the true sea surface elevation. And we can see true and predicted spectra, they are different, and predicted one is much lower. And also at the bottom plot, we can clearly see how it corresponds to the time series of the wave elevation. So we can see that the higher frequency components are just not predicted at all. And this weighting function or filtering function is just empirical function that we use that follows the normal distribution outside bounds of accurate prediction. And also for this particular source of error, we used we've done lots of sensitivities. For example, for one sea state, for 1 meter and 6 seconds, we investigated the different widths of the bandwidths, and also different starting and finishing frequency points of the bandwidths. Say, for this particular sea state of 1 meter and 6 seconds, we investigated if the waves are predicted accurately at 4 seconds only, and outside that is prediction is much worse. And this leads to the prediction error of around 6%. And this example, like 4 to 8, so we are accurately predicting in the bandwidths between 4 and 8 seconds. And we can see that the prediction error already drops to 3%. And for this particular case, if we predict only long periods, like 14 seconds, the wave prediction error is around 13%. So, and for each sea state, we investigated all those possible cases in order to understand which bandwidth is much more critical for our device. So which bandwidth is acceptable. This plot is also a bit busy, but I will try to explain. So this is the sensitivity study which I've done depending on, so we have a vertical axis as a normalized electrical power, and horizontal axis is finishing or this, the second boundary period of the prediction bandwidths. And each plot corresponds to the first period that we accurately predict. So say, for example, we can see that regardless the sea state, if we predict only 4 seconds, 4-second waves, then the power drop is quite significant across all sea states except 6-second wave period. But once we start widening the prediction bandwidths, the power performance improves significantly. And for this particular device, we can see that regardless the sea state, if we start predicting around 8 or 10 second peak wave periods, within like 8 or 10 second periods, the power production always stays within 95%. Similar plot, but it's across different significant wave heights. So electrical power production, dependence of electrical power production on the prediction error across different sea states and across different peak wave periods and significant wave heights. And similar trend as was observed as in the time delay case, that the power drops quite quadratically depending on the prediction error, approximately quadratically. And also the power decrease is not, power drop is not as significant for higher sea states as for lower sea states. So from this, from the limited bandwidth study, it was clear that if we want to accurately predict waves, we need to predict for that particular sea state, we need to predict its peak wave period and maybe 10 seconds below, or 2 seconds, sorry, below that. And for the C2 device in particular, we need 8-10 second period waves to be predicted accurately to stay within the bounds. And the last source of error that I investigated was prediction noise. So pretty much the wave elevation used by the controller is the same wave elevation as used as is going to the device, plus some noise, which is delta eta. And that noise we modeled also as a Jones Webb, like following Jones Webb spectrum. And we varied across different error peak wave periods of the error between 4 and 16 seconds, and significant wave height of that error was up to half of the significant wave height of the sea state. And this is just an example that the true sea state is 1 meter and 6 seconds, while the introduced noise was 0.2 meters and 40 seconds. And it was nice to play with parameters and find out the relationship between the prediction error and also that noise parameter is a significant wave height and a peak wave period, but not. So all the curves converged to a nice relationship, not really useful, but this plot is also busy, but the key point was that this is showing how the electrical power production depends on noise period and on noise wave height. And it was clear that the higher the waves in the additional waves inside the prediction signal and the longer the waves, the great electrical power losses become. So all those studies, lots of simulations and so on, but we needed to come up with only one magic number for this particular study. And Carnegie's device will be deployed in Spain at BMAP site, which has you can see the map on the slide, and the most occurring sea state is around 8 seconds and 1 meter. And we try to combine all of the parameters and all of that sensitivity studies into one nice curve. And you can see how normalized average annual electrical power depends on the normalized root mean square error of the wave elevation. And for across different modeling errors, time delay, bandwidth, and noise. So we could clearly see that regardless of the prediction or source of error, all curves kind of, I would say, converge. So in order to have a power loss not more than 5%, prediction error should be within 9% and not more. And also, you have to go deeper than the time delay should be less than 0.4 seconds. We need to accurately predict within 8 to 10 seconds, and prediction noise should be lower than 8 seconds. And if there is any noise in the prediction signal, it should be less than a third of the significant wave height. But also what was important to understand that all that study was done based on empirical data, empirical understanding of how the wave elevation error looks like. And it was a study done by the University of Western Australia, where they used an array of wave buoys in order to develop and test the algorithm, which is physics-based algorithm. And that wave array was deployed out of Albany, if I'm not mistaken. And when we asked the UWA people to analyze how the wave prediction error looks like, this is the spectra of those. Orange line is the sea state, and the blue curve is the predicted, is a spectra of the predicted of the error. I think blue curve, yes, is error spectra of the error, and we can clearly see that first, and also 4 plots correspond to different 4 instances. So error is not does not repeat itself, and it varies. Also, we have peaks in error close to the significant to the peak wave frequency, and we are trying to incorporate this data into our further study to understand whether any conclusions change. But I have a feeling that regardless how we model the error, conclusions might not change. I think that's it. Thank you very much.
Thank you very much, Natalia and Jørgen and Adi and James. So we've got a few minutes left for Q&A, and I can see that there's been a few questions that have come through. So let's start with the ones that came first. So I've got a question for Adi. Great results, Adi. What's next for M4?
Yeah, thank you for the question. So as I said earlier, so currently there's a lot of data to analyze. So that's ongoing. That's on the research front of things. I only showed like the motion aspects of it, but we haven't really looked into the mooring loads in detail. And also on the motion, there is also this phenomena of dunking that I briefly mentioned that needs a lot of work still. But you also asked about future plans in terms of deployment. We do hope that we can redeploy the device. That's for sure. In terms of modification, I think maybe not to the hull, but maybe in terms of the control aspects and the power electronics. I hope that answers the question.
Excellent, thank you, Adi. All right, next question is for James. So the question relates to, I mean, you've looked at a single converter. If you were to deploy an array of wave energy converters, what sort of impact would you expect at a coastline? Would it be sort of uniform and affect the whole coastline, or have alternative sort of impacts to the shore?
Yeah, great question. There has been quite a bit of, I guess, numerical studies into that sort of thing, particularly around the Spanish coastline, from what I've read. And they've used, different models to investigate wave energy converter arrays. And they do find quite a different result along the beach from some areas that have significant accretion or protection of the beach, and then some areas that erosion actually increases. And it's all dependent on how it affects the coastal currents in that local area. So yeah, something that hopefully we'll see more and more research of and start to get some measurements of that sort of data.
Excellent, thank you, James. All right, next question is for Jørgen. And it relates, you mentioned the sort of tidal regulator, and the question relates to whether there's also sort of an effect from currents.
Yes, that is correct. So there is, we still call it the tidal regulator, but it's set up to correct for also the horizontal mean displacements that we experience. So that would be from currents or from mean horizontal wave forces. So that's correct.
And maybe don't run away, Jørgen. We've got a sort of long question, which I think is relevant to all speakers, and it relates to sort of trying to understand the full environmental footprint across a WEC project lifecycle, really from sort of manufacturing all the way to sort of operations at sea. And Jørgen, I was wondering whether you could touch on the sort of aspects from manufacturing and supply chain, what are the sort of environmental footprints from those two areas?
Yes, so for the manufacturing and supply chain, I think that the main materials that we use, it's steel and the plastics in the composite. So there we try to work towards using recyclable recycled materials where that is possible, where the grade quality grade allows for that, and also to make the device in a way that it can be recycled afterwards. And that has been a challenge, especially for the composite materials. But in the recent years, there have been a very promising development within the wind industry that we are trying to learn from on the recycling of wind turbine blades. So that's it's certainly a challenge, but it's something that we take into account, at least in the way we plan the development. So that's for the You could also mention we have companyship with the Swedish steel manufacturer that is looking into carbon-free steel, so trying to do the full extraction and I don't have the words in English, but the fabrication of the steel without emissions. So that's of course challenging. I think it depends on all the processes also coming along on the path towards emissions reductions. And then to just briefly then also on the I think there was like environmental impact part of that question, wasn't it? Marine ecology. I think first perhaps I want to mention, I think, did we post the link? Yeah, so Jana, I think, posted a link there to this Tethys webpage, which is trying to gather experience from wave energy installations and tidal installations that we have. One challenge, of course, is that we are expected to know about the environmental impacts of this technology, but without having any considerable installations to base the learning on. But there are great efforts being made to do that as good as possible with the installations that we do have, and to monitor. So I think and there's a collaborative effort there to collect the data. So if you're interested in that, please have a look there. In general, I think depends which part on it you look. For the impact on different species, I think it can be, for example, from acoustic or electrical noise, it's very difficult to say something. From what I've learned, very difficult to say something general there, because it's very dependent on each species, what they are sensitive to. What can be said in general, I think, is that installations like this tend to work as artificial reefs, and to kind of make a protected area also, so that the trawling and fishing is excluded there, so that it ends up being like a protectorate for the life, and which probably makes the fishing very good at the borders of that area. So in that sense, it could perhaps contribute positively. But, it's just one perspective at least. Thanks.
Thank you very much, Jørgen. I'm afraid I know we could sort of continue these conversations for a lot longer, but we've actually run out of time. So I'm going to bring the session to close. I'd like to thank our speakers again. So thank you, Adi, James, Jørgen, and Natalia. It was a fantastic session showcasing wave energy domestically and what's happening globally as well. Please stay tuned for future webinars. This one, the recording will become available and then shared on the CRC website. And there'll be future webinars, obviously, later in the year as well. So thank you very much, everyone.